Good morning, good afternoon, and good evening, everyone. So today we're going to be using Newton-Raphson's method to approximate roots once again. But this time we're going to do it in nonlinear systems. So previously we did it through linear systems. But then not all systems are linear, right? Sometimes we have to deal with systems or systems of equations that are nonlinear. So let's say something like this, right? This one is definitely not a linear system. And so how do we solve that? How do we find x1, x2, and x3? Right? That's the thing that we're trying to get. I mean, those are the things that we're trying to get. So how do we do this? We can do it analytically, but sometimes again, it's not possible. As we've discussed in the previous video, sometimes it's not possible to solve these analytically using algebraic techniques. So sometimes we have to use approximating methods such as this Newton-Raphson method. And so we're going to do that. Okay. So since we already discussed this for a bit, I'm going to do a brief background of what it is to solve Newton-Raphson in multivariable ways, right? There's also one more thing. We haven't discussed how to solve a system, right? Mostly what we did in the previous video was we were given a function. We're given this function and we want to solve it using that method. So let's actually derive it when we're dealing with multivariables, right? So let's quickly do that. So let's do a background on, I'm going to call it multivariable Newton-Raphson, right? Because now we're dealing more than one variable. We're trying to solve a number of variables here. So basically to solve for this linear system. So here, let's keep it simple but general, right? I'm not going to go in depth as I did before because that one was personally, I think that was complicated. I have two functions here. I have two functions and they're both a function of two variables, but they're different. They're different functions. And so what again we want to do is we want to make a guess. So in the previous video, we said that, oh, okay, I have to make a guess in order to begin this method. So let's make a guess. Let's do some x vector. Here I make a guess of x and y, right? So I make a guess of x and I make a guess of y. They can be any. Honestly, they can be any. And we're going to use this formula here. We're going to use x n plus 1. I'm going to use n x of n minus j inverse. We'll get there on what j is. I'm going to get there in a bit. But we did discuss this, but I'll get there. And then this capital F, I'll get there to what this is. So now you might be asking, I'm getting there, don't worry. What in the world is f? I'll start with f first. F, this capital F, is actually just some function. This is what we call a vector function, right? So in this vector, I have my two things, my f sub 1 and my f sub 2. So I have those two things here. I have those two things here in my f. And then now what in the world is my j? So my j is what we call a Jacobian matrix. So we did talk about Jacobian iteration schemes. This one is a Jacobian matrix. Now, what in the world does this look like? Well, this is basically us taking partial derivatives with respect to the variable, right? So that's f of 1 with respect to y, f of 1 with respect to x, and same goes with f sub 2. That's it. And we can have more variables than just two of them. But in this case, we're going to keep it to two. So again, I was saying that we'll make it general, but we'll keep it as simple as possible. But this can go a long way. I'm just saying this can go a long way. I could have all the way up to of the n, right? I could have all the way there. But for now, we're going to keep it like this. And so my Jacobian matrix tells us, okay, we're taking partial derivatives with respect to x and with respect to y of both functions. Okay. And so let's go through an exercise here. What I'm going to do is find intersection of curves, right? And we're going to do this using Newton-Raphson method. And so here we want to find points of intersection between a circle and a parabola. As simple as that. So find point slash points, we don't know how many, of intersection of some circle and some parabola. Oops. And some parabola. So how do we do this? Well, so I'm going to go through coming up with the function. So my f sub 1 is a circle. This is going to be x squared y squared, or I'm going to make this minus 4, equals 0. This is a circle of radius 2, right? And then I'm going to get another function here. This is going to be x squared minus y plus 1, or actually minus 1, is equal to 0. This is a parabola. Okay. So I want to find the intersection of these two. Now, what we can do is we can solve this algebraically, but then we have square roots to deal with. So it's kind of impossible-ish, right? So here's what I'm going to do. I'm going to go through this exercise using what we just did before, right? Or what I've just defined before. So the first thing we want to do is define that function vector, this thing. And this contains those two things, right? So x squared plus y squared minus 4, x squared minus y minus 1, right? So this vector function contains those two functions of two variables. And then now I want to compute the Jacobian symbolically. So I'm going to do this analytically. And here I'm just getting partial derivatives. So based on this, I'm getting the partial with respect to x. So here. And that's just going to be, I'm actually just going to write everything. This is 2x, 2y, 2x minus 1, right? And then from there, I use my formula. So that's going to be x n plus 1, y n plus 1. That's going to be equal to x n, y n minus j inverse of x n, y n multiplied by my f, x n, y n, right? Because that's the formula we defined here. Instead of me doing one Newton-Raphson method, I'm doing it the number of times based on the number of variables. So if I have 2 variables, I'm doing it twice. If I have 3 variables, I'm doing it thrice. If I have n variables, I'm doing it n times. So okay, let's go ahead and look at the code for this. Let me show the code. Okay, let me just go to the thing and then just. So here's how it would kind of look like. Oops, I kind of, okay. Wait, is it? Can I see the screen? I don't know why I'm sharing, so I have to constantly check. Okay, there we go. That's the code. So we define the symbols and functions. My f is some matrix. I compute the Jacobian. There's a function Jacobian. Okay. I convert the numerical functions. And then Newton-Raphson. So I do it again and again, right? And so when I ran this code, here are the number of iterations. So at first, my x was 1, my y was 0. And then that's my f, which is 3. I keep going, and then I get, for my solution, my x and y. They intersect at these two. And we can see that through Desmos. So using Desmos, if I were to go ahead and try to plot this out, although I don't think it's going to be exact-ish. Let's try though. Oh, it's a 3D thing. Okay. I almost forgot it's supposed to be a 3D thing. Okay. So there's going to be some 3D quadric surface here. So what does this look like? X squared plus y squared minus 4. But they're equal to 0. So I have to look at it from the... There we go. When they're equal to 0, I'm just looking at this thing. Right? Okay. Another one was... What was it? So that was the circle. Another one was a parabola. X squared minus y minus 1. There we go. Should have just done it in 2D. Anyway, it was going to be 0 anyways. Okay, so here... Oh my goodness. Can you see... Oh, shoot. Okay, let me just do it in 2D. Whoopsies. That was... Okay, let me do it in 2D. X squared plus y squared equals 4. So that's the circle, right? Let me just double check if that's the circle. Yes, and then we have y is... Let me just put it nicely. There we go. So those are the two functions. And their points of intersection are specifically here. These two. This one, this one. And here, if we used that Newton-Raphson method, there we go. We have these two. Now you might be wondering, why didn't we take into account the negative? Well, I think that's one of the problems of using this method. So sometimes we don't take into account the negative, right? Or we just pick some point and then they converge, right? So if we were to pick a different initial point, then we probably would get that negative value. Like let's say if we do -5 or something. Can we change that? Let me see if we can do that. Yes, because here I started from 1, and then what I do? My y is 0. So what if, let's say, I start from, that way it would converge. I start from -2. If I do that, well, what's going to happen? Let me see. There we go. If I started from -2, I would get that negative value, right? I don't know, my y, let's say my y was 5 for some reason, if that makes sense. We still converge, right? Even though my y was 5, my x is -2, we still converge to that solution. the negative solution. So again, it really depends on where we're going, which direction we started, and then we will get to both solutions, right? But at the end of the day, it's just going forward. So as my x is increasing, it's going to stop when it hits a solution. So that's what the Newton-Raphson method does, right? So it just tells us, or it gives us an indication whether we're going to converge to a solution or we're not. But it doesn't tell us, oh, based on these two curves, there's exactly two intersections. It's not going to tell us that exactly. It's going to tell us, okay, based on the behavior of this thing, is it going to converge? Is it not going to converge? But it doesn't necessarily tell us that, oh, from here, I can already see that I have 2 points or two solutions, two intersection, 2 points of intersection. No, it only tells us that it's either going to converge or it's not. It's going to diverge. So it depends. Yeah. I think that's the basic idea of it, pretty much. That's the basic idea of Newton-Raphson method when we're dealing with what do you call this? Multivariable things. But yeah, that's pretty much it for that. Actually gonna try move to the next topic here. Like from here, I'm gonna move to the next topic. I'm gonna talk about approximating derivatives. And let's see if we can do something with this. Okay, so I'm gonna go ahead and go to exercises because personally I think this is really complicated. Let's try. See if you can move directly there. Okay, so just a bit of motivation behind it. When we're approximating derivatives numerically, it's actually also essential in scientific computing because computing analytical derivatives are hard or sometimes impossible, right? Okay, let's go ahead and attack an example here. So I'm gonna do this. So here, let's do an example. We're gonna use the forward difference formula, and I think we managed to. Did we do that somehow? Okay, we did more on Taylor series. Oh, there's what we did. So, okay. And then we also did some error analysis, which was very complicated. I was super confused. Okay, so here's what we're gonna do. We're gonna approximate our derivative. So instead of the limit definition, we're gonna take that one out, right? And instead we're gonna keep that thing there, but we're gonna take out the limit because that's the approximation, right? And let's say our f of x in this case is a sine of x. If we take a derivative, it's cosine, right? So let's actually approximate it using f prime of 1. Using that forward difference, let's say my h is 0.1, right? Because if we remember, when we're taking the limit definition of this thing, h is some small nudge, right? It's a small nudge that we add to x. And then as we're getting closer, or as h is getting closer and closer to 0, then we're going to get its derivative. But here, yeah. So, okay, let's go ahead and do that. So I'm going to try doing it in code maybe, or no. Okay, let's just, actually, no, this is easy using, yeah, so here we have sine of x. My h is 0.1, right? It should be super close to 0 so that we can get a better approximation. And so if we do f prime of 1, then we're doing this thing. So sine, I think this was Oh, what did I say? Okay, let's say my x is, yeah. So here my x is 1. So this is going to be sine of 1 plus 0.1 minus sine of 1 over 0.1. And that's around, what? 0.497-ish. But if we were to compute the exact derivative, that's going to be a cosine of 1, right? If we were to compute the exact thing. Cosine of 1, I believe, is just, oops, like 0.54-ish. I forgot what trig function that was. Cosine of 1 was, what was it again? God, it's one of these things. It was like a pi-ish, something with pi. Or there's nothing. Okay, it's a Taylor series. Ah, okay. There's an exact value. Huh. I was not expecting a Taylor series at all. Wait, is it just pi over 6? No, it's not pi over 6. Wait, what? Oh, for 1? What? Cosine? Wait a minute. Oh, cosine of 1 is, yeah. So cosine of 1, that's the exact value. I'm not gonna like go in depth on it. It's like 0.54-ish. So yeah, we need to get a closer and closer 0, or closer and closer h to 0, so that we can get a more or a better value, right? And so if we calculate this error, yeah, here I'm just gonna handwrite this because it's easy. This is 0.497 minus around 0.54 is like around negative 0.04, something like that. So that's our error, right? This is pretty straightforward, right? We're just approximating. Okay. And we can also do it the same way for different functions. So that's how that's one way of approximating, right? Okay, let's do the next exercise, which was, I think, about, that was the first one. The next one was, okay, this is mostly derivation stuff. So I'm not gonna go into the Taylor. You guys can watch it, but I wouldn't really recommend watching it. 'Cause it's very math heavy. It's more on deriving the formulas. So let's try something with central difference scheme. Now you might be asking, what in the world is that? What's the purpose of that? We're gonna find out here, like right now. Okay, I'm also gonna highlight this because I know we can approximate it when h is small. Okay, so those are the two things that we have to worry about, right? Okay, let's try that example. So let's apply this. Is this more effective? So what if you make use of this central difference formula? You can watch the derivation here in my previous video in my scientific computing series, but yes, we were able to derive such a formula that tells us this is computationally faster, if I'm not mistaken. 2h. Oh, shoot, I bet. X minus h. There we go. So we did derive that formula. Another way of approximating our derivative. So let's try that previous example. So this was sine x, right? Just keep it simple. And then my x is 1. And my h is, again, 0.1. Let's see. Is this better? So again, we approximate by plugging everything into our central difference formula. So we have we have sine of, I think this was 1.1, right? Minus, then this is 0.9 divided by 2 times this thing. And then if we compute all of that stuff, we're going to get 0.539 ish. And again, when we compute the exact derivative, it was 0.54. So indeed, this is more precise than just getting the slope. Or using that limit definition without the limit. This is more precise. Right? How were we able to derive this? I'm not going to go in depth, but basically we did some Taylor series. And as we did that, we get a faster convergence rate, which in this case, I think it was 2. We did get that. And the error goes down at a faster rate. So this is what I'm saying is that the the center difference scheme is way, way faster compared to our original approximation up here, right? And so obviously, if this is faster, then lesser error, right? We can just calculate the error by, well, oops. Also, I forgot to mention, well, if we're calculating the error, we want to get the absolute value. So I'm just going to say 0.04, right? Just to make it friendly. So we're going to be, so our error is this minus 0.54-ish, which is again around like what? I'm not putting the full numbers, like, yeah, like 0.0009-ish. So it is definitely better than the previous one. All right, I think we can, let me copy and paste the code for both. So I'm going to show you guys what it looks like for the first approximation and for the second approximation. I'm still in the root finding thing. Let me go ahead and take all of these out. Copy paste. There we go. So for the first one, yes. So that's us approximating. And here, we're actually picking h as it gets closer and closer. And we see here that, actually I can't see because of my sharing. So here, as we pick an h that's closer and closer, our forward difference, or the first approximation that we did, well, its error is decreasing, right? Error is decreasing. But if we use the central difference, it's actually way better. -9. It's getting better and better, right? So central difference is way better than just a forward difference. And I think I can show another code for that, kind of. Oh, that was for all of the, oh, so I did for all of the thing. Oh wait, that was it. That was all of them. Yeah. And then another technique here was getting the second derivative, which wasn't as, oops, why am I annotating? Which wasn't as effective, kind of. Let me see my screen here. Am I showing the right thing actually? Oh yeah, okay. So let me see if that was in my notes, because I don't think we discussed that, or did we? And I just totally forgot about it. Oh, so we didn't do it yet. Okay. Yeah, that's gonna be in the next video where we're gonna approximate second derivatives. But for now, that's the basic idea, right? We're saying that, okay, it's way quicker. The convergence rate is twice, or not really twice, just twice here. The mathematics behind it Well, it basically tells us that this center difference scheme is faster when it comes to converging to a solution, right? It's faster when we're getting to its derivative compared to the forward difference where we just take out that limit. Yeah. Okay. At least I boxed it in blue, so now I know where to look at it. Now I know where to look for it. So this one's way faster, right? And then the next technique, which I kind of showed it already in the code, wasn't supposed to do that, is I'm gonna go through a derivation of derivation. Yeah, how do we approximate second derivatives? Right? We're gonna analyze all of that from top to bottom. I'm also gonna be confused at first, but we're gonna get through it. Yeah. And then I'm gonna include some examples along the way to make it more engaging. Anyway, I hope you guys enjoyed. And this is really interesting stuff because again, not all things can be solved analytically. Sometimes you have to do it numerically in approximate manner. And so that's why we're developing these applied mathematical methods to do the following things. Anyway, that's it for this video. I hope you guys enjoyed, and I'll see you all in the next one.